Very good afternoon to one and all present over here. Myself as Tamilselvi, under the guidance of S.M. Kerala sir and Hoshiar Singh sir. I would like to present my paper on the title, A Study on Medical Image Denoising by Using Filtering and Transform Methods. Basically, before going into the thing, this is just an overview of my presentation. So objectives, introduction, and literature review, and different types of noises, methods of denoising, and some experimental results has been taken, and conclusion also has been found from that. Quality also has been checked, and the most important thing of my presentation is that is I want to have a appropriate hybrid techniques which can preserve all the fine details and edges or contours of medical image. Why I have chosen this topic is basically nowadays that is diagnosing of an accurate disease is very, very crucial. Once diagnosis comes properly, then only the right medicines or whatever the treatment can be followed. So for that, even in a COVID-19 period, many times the doctor has whether it can be this type or that type, the suspicious was on. So for that, this denoising of an image, medical image, especially if we consider, and some of the high, even though many older techniques are there, if we could concentrate on some of the hybrid techniques, which is very much the cost efficiency as well as the computational time is reduced. That's the objective of this. And after, even though the diagnosing is done, the quality of the images has to be measured and it has to be in a proper ratio of conclusion. If denoising is done and quality is not appropriate, then also it is not good. So these are the three major objectives. And so coming back to our the topic, so basically what is denoising? Denoising is not just something we are just removing some of the high frequencies from our, because whenever we take any digital image for this matter, if we are removing the high frequencies and that keeping the lower ones, that is not called as a denoising. Because whenever in that process, when we are removing that, it should not affect the details and fine, especially medical images are concerned, the minute, the finer details will give you the more accurate diagnosis. So that's why it is not just removing the high frequencies, and not only in medical images, whether you have the satellite images or data mining or data astronomy, this denoising of an image plays a very important role. Next is the noise model. So basically, what is noise? So whenever you have an image, any kind of image, if some of the noises are there, there can be why these noises occur. Basically, we know we are taking in very good pixel, the images are very proper. Of course, nowadays technology has been advanced and many things are in advance, but still, due to some low light, even in electronic machines, any type of machines, if you take in digital machines also, due to electronic inferences or the low light intensity, sometimes some error can occur, and due to that noises are available in the images. So in noise, when we are comparing a noises, there are basically two types of noise models. One is additive noise and other one is multiplicative noise. But this additive noise is quite what we can say, it is in a simple way to denoise, whereas this multiplicative noise is a little bit difficult for denoising purpose. And in most of the medical images, so here I have expressed some of the noises. This salt and pepper noise is an example for additive noise. That is, the black and white pixel dots are mainly occurring in the images. And this mainly causes due to the sensors, defective sensors in the camera or some faulty memory locations, etc. But the next example for an additive noise, we can have it as a Gaussian noise also. But this speckle noise and Poisson noise, these two noises are multiplicative noises. When you are comparing additive noise and multiplicative noise in an image, and when you are concerning about the denoising, it is little bit difficult because the quality as well as the denoising purpose, it is not, denoising is means it is not completely removing. Up to a certain extent, we can reduce the noise, suppress the noise, so that we can get a quality of the image in a proper way for diagnosis. So there are various different methods available. Even from the literature curvature, I found that there are various different methods available. Filtering methods are there, and transform domain methods, statistical methods, machine language methods, and nowadays even I think one of the presenter also previously when I was just listening, they have applied a deep learning also. So even as technology advances, the methods also investing. But my aim is I want to have, because every advantages have some, every method has some advantages as well as disadvantages. But I want to have the main aim as the computational cost should be less and time is the most important factor, especially in finding out, identifying a disease. The time plays a very important role and it is very, very important. So this filtering methods is a old traditional methods which we can say. And in traditional filtering methods, we have two types of filters can be used: linear and non-linear filter. So basically, in my paper, what I have identified and I have experimented with some of the filters of linear as well as non-linear with the images, medical images especially. And I have applied some of the transform methods also. And we will further, when we go to the slide, we will see all the experimental details and the results which we got. And so in transform methods, domain methods, if you go in detail, we have various different transforms: Fourier transforms, wavelet transforms, dual tree complex wavelet transforms, curvelets, ridgelets, riplets, counterlets, shearlet transform. So even though these many transform methods are already has been used for the purpose, but when we are using, what is my thinking and thought is, when we are applying a hybrid model of any of these things, then that will be giving us a better results. So this will go some of the literature survey. First one is the traditional filter method, that is the filtering method. So the first one, averaging filter. The methodology used is just replacing each pixel by average of pixels, but in a square window. That is the most important thing. And in that case, whenever we are applying the average filter, even in my experimental results, we can found that the edges are blurred and it is not at all effective in some type of noises, because it's not like that we will have always a particular type of noise in an image. So I have experimented with various different types of noises, as additive noise as well as multiplicative noise. And then in median filter, then this one example for a non-linear filter is a median filter. So this median filter takes the median value instead of the average. So it has better an advantage of than this averaging filter. But here also limitations are there. The corner, that is the edges, are not preserved. So even some of the things, some of the images, the doctors are very keen to observe in the edge, what is there in the edge, exactly in the corner. Then in the transform methods also, some of the literature survey which I have done is, first in Fourier transforms, they have applied, and then in that it is basically, it is only working only in the stationary signal, and it is not useful for non-stationary signal. But we cannot always say that whenever we are taking an image, it will be only a stationary image. It is only about the time domain here. Then comes the wavelet transforms. It is more advantage than the Fourier transform. What is that? It is working in the both the domains, that is the time frequency, time as well as the frequency domain. So here in wavelet transform, what we can do is we can just define every in all directions. We can just in horizontal, vertical, diagonal, like that, in all the directions. We can take that is plot into the images into the smaller way, and finally we can have a better results in wavelet transform when compared to the Fourier transform. But here also, whenever discontinuities occurs in some curves are there, that is some contours are there, that time it will be not helpful. Next, the counterlay transforms. Here also the quality denoising is happening, but the higher here you are to remove the Gaussian noises, it is used. But especially in medical images, we have speckle noise, which is a multiplicative noise. This is not suitable for that. And curvature transforms, it is very useful in representing the edges and curves, singularities much more efficiently, but it it handles the curves using only the small number of coefficients. When it is handling with the limitation of small number of coefficients, it will be difficult for a view of very large images which is compressed for medical, because nowadays we are sending the images to other countries all over the world in a compressed way. So for that also, if your denoising is done by this curvature transform, that large number of coefficient in compression, it is not efficient. Then comes the Scherler transforms. Sorry. In Scherler transforms, optically sparse optical. Actually, this is one of the best transform nowadays, which can be applied for denoising techniques, because in this Scherler transform, there are no restrictions in number of directions of sharing, and it is a multi-resolution and multi-directional. So both the ways we can have n number, no constraints on the size of the supports of sharing. So it is having a very good future, geometrical features, and it handles the images with multi-direction and as well as the in multi-angle. So it is a multi-resolutional analysis. So these are some of the literatures. After finding all these studies, I just thought of checking the quality. What are the many parameters are available? See, PSNR, that is and MSE or the error metrics used to compare. This are the some of the image quality. That is one of the image quality metrics which I have tested for my testing images. But this PSNR refers to a peak signal to noise ratio, and mean square error is just before also my one of the presenter has been used mean square error as well as this mean absolute error. These are all very good error metrics. And so whenever this mean square error is when we are comparing the original image and the denoised image, what is the error, what is the ratio of error we got. Based on that, we can conclude the image quality. And the peak to signal to noise, it's not like that only PSNR and this mean square error is only available for image quality metrics. Apart from that, we have nowadays the structural similarity index measure, which is one of the most widely used for especially the color images, because nowadays the color X-rays are also available. Even in CT scan, this color images they are providing. So for that, the illumination, similarity index, structures, everything can be tested. The quality can be tested by structural similarity index. So here the PSNR value usually is calculated in decimals, and the next we'll see some of the experimental result. This is an experimental result which I have just given you a picture over here. And basically in a Kaggle data set, I have taken some of the this X-ray images, COVID X-ray images as well as normal X-ray images has been taken. And in a MATLAB simulation, I have just given that, and it has been tested. The images has been tested with various different types of noises, salt and pepper, Gaussian noise, and with the different variances also. And but here for time restriction, I have just given you only the speckle noise. That is, speckle noise is a granular noise. So granular noise is quite often observed in medical images, and we have to focus on speckle noise rather than the additive noises like other noises like salt and pepper and all. So that's why I have given this only. And after applying the average filter in the speckle noise image or X-ray image, average filter, after applying average filter, the denoised image is given as well as the median image is also given. But when I check the quality for all these things, that is by using the mean square error as well as the PSNR ratio has been calculated for this. So this image also this filter, that is the Gaussian filter and Wiener filter was also applied and checked, because by using various noises and various filters, first one set of images has been experimented, and in the next experimental results, what I have taken, that has been taken in the transform side, that is original image, and then these noises. Just you see the noisy image here. Here I have added the intensity more of a speckle noise, and here then in the third image, that is we are using that vertical component. So first horizontal, vertical, and then diagonal, all the component has been used, and finally after applying all the components of denoising by using the wavelet transform, the final image, the original image is this, and then the wavelet image is this. So even though here I think the original image, when you see, they due to some luminous effect, it is not that much clear. So after denoising and with the help of wavelet transform, the image is very clear, and the quality has been checked. This is the image quality metrics which I have been checked for the various filters applied in the image, that is in the noisy image after denoising. And here the points which we have got, which we can conclude, that is the peak signal to noise ratio, which is represented in decimals. That is, the higher the PSNR will give you the quality more. So when you compare the results of filter and wavelet transform, that is here wavelet transform is 44.29 and median filter. Median filter is a non-linear filter. So the conclusion is that error also, when you are comparing that PSNR, the same time error should be minimum and your PSNR should be at higher range. So that will give you this is some sample image quality metrics has been taken and tested over here in the experimental result. And so conclusion of this is, after applying the additive noises and multiplicative noises in various, we found that the nonlinear filters work better in speckle noise and wavelet transform making more better. But still, the most important thing I have told in the beginning also, I want the objective. The objective of my topic is that I need a technique which is the hybrid model of a shearlet and curvelet transform. Because curvelet transform, why I have chosen this hybrid model means curvelet transform can be used for the edges and curves, and the shearlet transform is has a multi-directional and multi-resolution. So higher the PSNR, good quality will result in that. So that is the next experiment which I am going to in the new model. This was the study has been taken with all the different types of noises and transform. So this paper has been done, and these are some of the references.
Thank you.
Okay, thank you, sir.
Thank you, ma'am.
Thank you.